Hi everyone, this is Mr. Lee. In this video, I'm going to go over the QQT problem that we did on Tuesday. All right, so in that QQT problem, we have a rod and we have a disk, right? And then we have this point called C. And so part A asks, where should this disk hit the rod in order to create maximum rotation? All right, so here's a couple of things. This is a little bit off on the side, but these are like the star kind of ideas. Star idea number one, whenever there is a impact of any kind, the first things that you should always think about is the conservation of momentum, okay? Just have your mind go there first. Now, because we're talking about conservation of momentum, if you're thinking about this, like it could be like a rotational thing, or it could be like a linear moving thing. But if you start to think about the conservation of momentum, usually all of the variables that you need in order to explain it all fall into place. So we know that the conservation of momentum is, I'm going to do it in linear form first, is that your initial momentum has to equal to your final momentum. If this is not the case, then we have what we call impulse. So impulse is equal to force times the change in time, which is equal to the change in momentum, right? So this is if momentum is conserved. This is if momentum is not conserved. Now, the only way that you can know if momentum is not conserved is by looking at the system, right? How did they define the system? All right, so from here we can do the rotational style. All right, L initial is equal to L final, and from there I'm just going to do a little side note here and also a little side note there that momentum is mass times velocity. Here rotational momentum is I omega. Okay, so that's if you have an object that's rotating. So this is a object that is rotating, and we also have this new form MVR. This is for object moving in a straight line. Okay, so we have two forms of L. All right, so with that, we can come up with the impulse for rotational momentum. So instead of saying force, we can say torque. So torque times time is equal to delta P. Now this is where the equations really help you, because we know that torque is two versions of torque, and I'll do this as a little sidebar. Torque we know to be F times R, or I times alpha. And so we usually use F times R when we are looking at an object that is being struck from a certain radius away, right? Just like in our problem here. So what I'm going to do is I'm going to rewrite the impulse equation so that we can actually answer this problem. So F times R times T, okay, frat is equal to, oh, that should be delta L, excuse me, not delta P, delta L. So if we take a look at this, the question for A asks, we want the greatest, I guess it was rotational velocity, omega. All right, so we take a look at this equation, F times R times delta T, and we know L is I times the change in omega. Okay, so we want the greatest, I'm going to highlight this, we want the greatest omega. So in order for this to be the case, we don't know anything about the impact time, so we're going to ignore that. And we don't know how hard it's going to be hit, but the only thing that we do know, and that's what the question is asking for, is what radius should the object make an impact. All right, so the reason why I highlighted both of these variables is because if you look at A, okay, question A, your answer choice talks about the striking distance. Oh boy, triangle, striking distance. Okay, so that talks about the striking distance, which is aka R, and in order to have the greatest rotational speed, okay, so we want the greatest. So here we have a directly proportional relationship. In order for this to go up, because omega and radius are directly proportional, we need to have the greatest radius, and that is why for A, we say that it is to the right of C. So to the right. Okay, so right around here is where we want to hit it. So if we take a look at the answer key says anything along the lines of, if you talk about this equation as a whole, okay, you get a point. So I'm going to break this up again so that we get torque times change in time is equal to the change in angular momentum. And I'm reading the answer key, which you all have a copy of. It says that the torque exerted by the disk, okay, so torque, if you talk about the torque, or the angular momentum, so here we have angular momentum, is greater when it's further from the pivot, and so that's where we have the R, right? So if you're talking about the different variables within the equations that you've chosen, you are guaranteed to get the point. Okay, so in order to have the greatest torque, you need to have the greatest radius, because the greatest radius will give you the greatest rotational velocity. Now, they did have a little caveat there that says don't manipulate any equations. So all that means is don't write out any equation. Okay, they don't want you to write out any equation, but instead what you have to do is choose the equation that you want to talk about, and then just talk about it in terms of the variables that you need to talk about. All right, part B. So the correct answer is yes. Now, I'm going to write down the made-up equation that they gave you. So this is the first time we saw anything like this. Okay, this is the first time we saw anything like this, where they came up with a equation, x, v, o, and I. And so for B, it says, regardless of whether this equation for angular speed is correct. Okay, so that one of the first thing is that they're telling you that it's correct. It's saying, does it agree with your qualitative reasoning in part A? Okay, so qualitative reasoning. Now, if you remember, QQT stands for qualitative, quantitative, and then the T is the translational, right? And so what they're saying is here we have a very quantitative question, right? We have an actual equation, and so part A is this qualitative. It's the conceptions behind it. It's the idea behind it. So does this equation, this quantitative equation, match what you thought to be true? Okay, so that's how the Q and the Q, they link together. And so whenever they ask you anything like this, whenever they give you a made-up equation, they're like, does this make sense? What you have to do is you have to see, all right, based on what I answered before, are my relationships true? So if you remember part A, we were talking about the radius or the striking distance. Now for this problem, they didn't use R, but they used X, okay, and the rotational velocity, which is omega. So ignore all the other variables in there, because you don't have to worry about them at all. Instead of using X, I'm just going to cross it out like that. Okay, so you're only looking at the equation like this. The other variables there are there to distract you. So if we say that our striking position increases, that means our omega should increase, and that's because it's directly proportional. All right, and so we would say yes. Okay, now mind you, you don't get a point for just saying yes, but one, you get a point for linking what you said in part A to part B, and the second point talks about as omega increases, we want a greater X, or a striking position, right? So, and then we can say something like, because according to the equation, these two are directly proportional. They love it. It makes the grader's life so easy when you use language like this. All right, now let's take a look at part C. Part C, they throw a curveball at you. Okay, we're not used to seeing incorrect equations. So I think part C is a little bit more difficult because of that reason. We have omega is equal to I, the striking distance, the linear velocity all over the mass of the disk, times this d4, okay, the length of the rod to the fourth power. Now, I think I did mention this in class, but when I first saw this problem, I was so thrown off by this d to the fourth, because I've never seen anything close to this. And in fact, if you look at the answer key, they tell you that if you talk about this, you don't get that point. They don't want you to talk about the idea of, well, technically, you can't have a fourth power of a rod. You can't. You just can't. It can't happen, right? You can't talk about any of that because they don't care. They don't care about it. They know this equation is wrong, but they want to know the reason why it's wrong is of the physical reasons behind the equation. And anything that talks about that is talking about the relationships. Once again, relationships. Okay, what's going on with the relationships? And so here, what we look at is we don't look at the striking distance because this makes sense. Okay, you know what? If I can write that down, we know that okay, this is directly proportional. Okay, and this makes sense. As the striking distance increases, so should your omega. So we don't want to talk about that. We don't want to talk about this. Okay, and the other one is omega and velocity. Okay, so this should make sense, right? If the disk is moving faster, okay, if the disk is moving faster, that means the rod will spin faster. Okay, so that makes sense. We don't want to talk about it. We don't want to talk about anything that physically can happen. All right, and so the other ones that we can look at is omega is equal to I, omega is equal to m, and 1 over m. I'll just say omega equals m, and of course omega is equal to d. All right, d to the 4th, I believe. Yeah, and we'll just call it d. All right, so from here, I want to choose the one that makes sense, like, you know, because I want to eliminate it like we did earlier. So what this is showing us is a inversely proportional relationship. Okay, we have an inversely proportional relationship here. And does this make sense? And the answer is yes. If we have a super long rod, okay, that means the rotational inertia will increase. Okay, if the rotational inertia increases, okay, it's not going to spin as much. So this checks out. Okay, so this, we can't talk about it because that's a true statement. However, these two shenanigans over here do not make sense. So what we have here is, according to the equation, this one is directly proportional and this one is inversely proportional. So what this is saying is if you have a very massive disk, okay, a very massive disk, and it strikes a rod, that means it'll spin slower. What? That doesn't make any sense. All right, and so for this one, we have I versus omega. This is saying that if we have a super heavy rod, okay, and we have a disk that strikes it, that it means that the rod will spin faster. What? That doesn't make any sense at all. Okay, so these two are the relationships that we're looking at. My strategies of going about it is I looked at every variable, okay, and I said, does this make sense? And the other variables made sense. And so if you talked about either one of these two, you would get the point as long as you're talking about relationships and relationships only. All right. I don't want to go over D too much because I do have the way that you would solve for it. Just so you know, once again, if you have any type of collision, okay, automatically brain, is it energy or is it momentum? Okay, now chances are, okay, if it's a collision, it will be a momentum type of problem, and so in the answer key, I do go over how to solve it in that fashion. Okay, so the last one I want to focus on is E. All right, so for E, it says consider the collision for which your equation in part D was derived. All right, so you came up with the derivation. Now let's say you totally skipped D. That's okay. You can still answer E and get points because E, we're talking about a inelastic versus elastic collision. Okay, and it's saying in which scenario will the post collision, so VF, okay, VF. Or in this case, omega f, which one will be greater, right? Will it be the elastic or the inelastic? Now this is this is just physics, okay? For an inelastic collision, kinetic energy is lost. Okay, if kinetic energy is lost, that means the velocity decreases, all right? Because we know kinetic energy is equal to 1/2 mv squared. For rotation, kinetic energy is 1/2 I omega squared, right? And we're talking about omega here. So if kinetic energy is lost, boom, it gets slower. Now for elastic, kinetic energy is conserved. Okay, kinetic energy is conserved, so no kinetic energy is lost. Therefore, the velocity, okay, it doesn't remain equal, but because it doesn't decrease, the velocity will be greater. Now, let's figure this out. Okay, let's figure this out just conceptually again because it's good practice. Now, I'm not going to do a rod and a stick. I'm just going to do two carts. Okay, I'm going to do two carts here. So let's say we have cart 1, M1, and we have M2. Let's say M1 has a velocity going forward, and let's say M2 is moving or it's not moving at all. All right, now I'm going to come up with the two scenarios. I'm going to draw an arrow. This is the inelastic. Okay, so in the inelastic, the two carts, they collide and they stick together and they move off in one direction with the same final velocity. All right, so if we are creating an equation for this, we would say the initial momentum of 1 plus the initial momentum of 2 is equal to the final momentum of both objects. m1 v1 plus m2 v2 is equal to parentheses m1 plus m2 v final. We know that v2 is 0, so it'll just be m1 v1 is equal to m1 plus m2 vf, and we want to look at the final velocity here, so I'm going to divide both sides by that parentheses. We get m1 v1 all divided by m1 plus m2. Okay, so we have vf that looks like this. All right, now let's do a elastic collision, okay, where they hit and they bounce off. Now, to make things easier, let's just say that they bounce off with the same velocity. All right, so they hit, m1 is going to go this way, and m2 is going to go this way. All right, so we want to know the final velocity of m2, right? So here we're going to start off our equations the same. m1 v1 plus m2 v2 is equal to m1 v1 final plus m2 v2 final. All right, so we have something that looks like this. Let's make this a little bit more clear. This is 0 because it's not moving. So we get m1 v1 is equal to m1 v1 final plus m2 v2 final. We want v2 final. So I'm going to do some algebraic manipulation. I'm going to move m1 v1 f to the other side, so we get m1 v1, so this is initial, just to be clear, minus m1 v1 final is equal to m2 v2 final. I'm going to divide both sides by m2, like so, and so we get our final answer of vf is equal to m1 v1 initial minus m1 v1 final, all divided by m2. All right, so if I take a look here, this answer versus this answer up here. All right, so if I take a look at both of these answers, the reason why this final velocity, oh, you know what, I forgot something here, because m1 is moving to the left, this should be over here, m1 v1 final, this should be a negative m1 v1 final, excuse me, pardon my French there, I made that mistake. So if we move it over side, this should be positive. Okay, so I fixed my mistake. Okay, all right, so if we take a look here, the inelastic collision, and by the way, this is something that you should memorize. This inelastic collision, we have a big denominator. Okay, so denominator. All right, there we go. All right, we have a big denominator, and here, because the two factors are adding, we have a big numerator. All right, we have a big denominator and we have a big numerator. So mathematically speaking, if we have a big denominator, we approach 0. If we have a big numerator, we approach infinity. And I don't know about you, but I do know that infinity is greater than 0. Okay, and therefore the elastic collision, I'm gonna make this big. Okay, I'm gonna make this pretty for all of us. All right, using my Galaxy pen because this is very mucho important. Please, students, my wonderful students, know this. Elastic collisions always have a greater VF. Always, always. Let's get more rainbows in there. That's kind of hard to see. My mistake. All right, elastic collisions always have a greater final velocity. Anyways, this was the first QQT that you saw. We're going to do another one. If you watch this video and you really internalize what I'm saying, it should definitely help you out in the future. I'll see you then. Bye-bye.